Hello everyone, I'm Zaira Pindado and I'm going to present this paper, Simulation Extractable Versions of Groth's Zero-Knowledge SNARK Revisited, which is a joint work with Karim, Baghery and Carla Ràfols. We start talking about non-interactive zero-knowledge proof systems. In these primitives, the prover's goal is to combine the verifier that some public statement X is valid for a relation R without revealing its secret information that we call the witness. In non-interactive setting, we have just one single message. In the CRS model, the prover and the verifier receive the same common input, that is the CRS. The prover uses it to compute the proof, and the verifier uses it to validate the proof. These proofs have three fundamental properties: completeness, soundness, and zero-knowledge. Completeness is the property that guarantees that the proof should be convincing for the verifier as long as the statement is true. Soundness guarantees that malicious provers could not convince the verifier of false statements. And zero-knowledge, that no extra information is leaked from the proof beyond the validity of the statement. We want to talk about the SNARK, so we give the following notion first. When the proof is sound against adversaries with computational power, we call this proof an argument. On the other hand, a strong notion of soundness is knowledge soundness, where we prove that not just the relation holds, but also the prover knows the witness. And we formalize it using an extractor. Why? Because intuitively we consider that a machine knows something if this machine is able to output it. So, if the adversary sends a proof that passes the verification, then the extractor that in SNARKs we consider that has access to the source code of the adversary is able to output the witness efficiently. Zero-knowledge SNARKs are the non-interactive zero-knowledge arguments of knowledge that are succinct, which is that they are very short and the verification process is very efficient. Then, SNARKs are the most efficient non-interactive zero-knowledge proofs in bilinear groups for general languages, in terms of proof size and verification complexity, which is very useful for applications. For example, they are widely used for correctness of computation in applications like blockchain, where a huge amount of SNARKs are proving the correctness of transactions that should be verified. So any improvement, even if it is very small, is very important. SNARKs are defined in bilinear groups. We want to note here that we will use bracket notation for elements in the group. This notation is taken from elliptic curves, where the elements are points. If you want to compare with multiplicative notation, we will use the exponentiation to the generator instead of the addition. Now we focus in the most efficient SNARK that was presented by Groth 4 years ago, and it's widely deployed because its efficiency. The proof is just 3 group elements, and the verification consists in 3 pairings. However, its knowledge soundness is proven in the generic group model. We are not going to give details of this scheme, but we want to note the role of the element delta that is given in the group in the CRS, and it's used by the prover in each element of the proof, A, B, and C, to add the randomness and completely hide the witness, that is this vector of A's, and this will give us the zero-knowledge property. This delta is used as well by the verifier to verify the proof. However, this SNARK is malleable, as is noted by Groth and Mahler. because if an adversary eavesdrops a proof generated by an honest prover, it can generate easily a proof like this, where R is chosen by itself, which will pass the verification equation. So if we classify the malleability in these two types, randomizing a previous proof and obtain a new one for the same statement, or creating a new proof for false statements, this case of Groth will be in the first case. In some applications, there is no problem with that, but in others, like signature of knowledge, for example, that we have a SNARK linked to a message, this will be a problem. So we focus on this property, simulation soundness, where an adversary cannot cheat even if it has seen simulated proofs. As we have knowledge soundness, if we add simulation soundness, we will have this strong property that is simulation extractability soundness, with knowledge and simulation. Just to note that there exists the notion of weak simulation extractability, which allows proof randomization while it guarantees that a proof cannot be changed to prove a new statement. Baghery et al. Recently proved that the SNARK of Groth achieves this type of simulation extractability. But in our result, we want to prevent all kinds of malleability. So our goal is to modify the Groth SNARK to achieve simulation extractability with similar efficiency. We are interested in the minimal overhead respect to Groth. We present some works that propose alternative version of Groth with this property. We start with Groth and Mahler, where they double the size of the CRS and the prover complexity, and also they add 2 pairings in the verification. Then we have Bowen-Gavison, where the CRS and the prover complexity is the same as Groth. They add random oracle to the proof, and also 2 elements to the proof and 2 pairings to the verification. We have another result by Libma that has a bigger CRS and prover complexity. The proof is increased by 1 element and the verification by 2 pairings. We have a Tapor and Baghery that has a bigger CRS and prover complexity. The proof is increased by 3 elements, but they have this nice feature that they just increase in 1 pairing, but they change the language. So here we emphasize 2 nice features from Bowen-Gavison, that they has the same CRS and the same prover complexity as Groth, but they add this random oracle. And also we want to emphasize that at Tapor and Baghery increase the verification in just 1 pairing. In this result, we propose a construction where we increase the proof in 2 elements. We increase the verification just with 1 pairing, and we have very similar CRS, but we increase just in 1 group element. This result is based in Bowen-Gavison result. It's very, very similar. But we avoid using the random oracle by a change of increasing the CRS, but it's just in 1 element. We also want to know that we have another construction that is in between Bowen-Gavison and this result presented here, where we have the random oracle, we increase the proof in 2 elements, and the verification in 1 pairing. The idea of Bowen-Gavison approach is to randomize the parameter delta. and also give a proof of knowledge of how they randomize it. This delta is given as in the SNARK of Groth in the CRS. Then the prover samples some element zeta and uses it to randomize this delta. And it uses it in all the elements of the proof. Then the proof is the same element as Groth, also this delta prime, that is the randomization, and the proof of knowledge, which has this shape, where ys is the output of the random oracle. And the verification has the same equation as Groth-SNARK with delta prime and this other validation, which requires two pairings. We have a very similar idea. We randomize the delta with the z, and we give a proof of knowledge of it. The prover and verifier computations that in Groth-SNARK were with delta, now we replace by this delta prime. So it's the same approach, but our proof of knowledge is a signature that is a variation of one Evoyen signature that just requires one pairing. The proof of knowledge that we use in our first approach has this form. Why we say that this is a proof of knowledge of the discrete logarithm of delta prime? Well, let's see if we design the proof in the interactive setting where 1 over delta is given in the CRS and the prover commits to this delta prime, it receives a message M from the verifier and finally sends this element with delta prime plus delta M in the denominator. The intuition is from this element 1 over delta, the adversary can compute just combinations of it. So to come up with something like 1 over a sum of delta sum some C is because it knows a relation between this delta and this C. So if the adversary gives this signature, is because it knows a relation between this delta prime and this delta. So equivalently, we can say that this is the proof of knowledge of the discrete logarithm of delta prime respect to delta. This is the first construction where this M is output by a random oracle. Our second approach, which is given in this result, uses the collision resistant property of a hash function that outputs the message M. How we avoid the random oracle? Well, we introduce a new variable, gamma, that forces the adversary to construct these two summands. The idea of why this is a proof of knowledge is very similar. The adversary should know a relation between delta prime and delta and use it in both summands. We want to note that this proof of knowledge is not zero knowledge. The whole SNARK is zero knowledge, and we can simulate it. But if we just look this subproof, we don't need to simulate it because everybody can randomize delta. Okay. The soundness proof of our SNARK is proven in the generic group model. First, we use the proof of knowledge to extract this discrete logarithm, this zeta. We extract it or we rate the collision resistance of the hash function. In the second step, we reduce to the knowledge soundness of Groth. How? First, we prove the elements involved in the SNARK of Groth are computed without using elements of the simulation proofs. So we can reduce our proof to the knowledge soundness, just adjusting this change in the delta. Thank you for your attention.